All right, welcome back, everyone. We're kicking off our next session. We have here Gans, who's going to be giving a great topic on multimodal data aggregation and causal inference, applications to cancer. We were just speaking before the break. A lot of new cutting-edge research. He'll be talking to you about some of that today. So let's give it up for Gans.
Thank you, folks, for trading your afternoon for this talk. Hope it's useful. So once again, thanks to the sponsors and the organizers. So what I'm going to talk about is divided into 3 segments this afternoon. It's more of what's to come in a nutshell. How many of you have heard the theory of causality? Sure, you're from Columbia. Absolutely. Great. Okay, so we will cover how, precision medicine. How many of you have been indulging yourself in precision medicine area? Okay, I just want to get a feel. Great. Thanks again. So with no further postponement, let's start the process. So I have divided the talk into 3 portions. First, a basic introduction of where the technology is going, what the health industry needs, and whether the timing is right. Are we solving today's problem or tomorrow's problem? If you're trying to solve today's problem, you are too late. There is no money to be made. So that's another point. Then let's give an introduction to the data science, basically what the causal inferencing is. All of you might have heard about AI, but let's get into the definition of what the causal inferencing and causal theory of causality. And I will also go through a primer, because Michael really wanted me to do a primer. I don't know whether I put you to sleep or I put you to some equations. Let's see that. And then finally, I'll give you a real-world problem, which is basically how we have taken actual data. I have de-identified the data from a real hospital system, so they are not fictitious data. So that's the outline of the talk, 30 minutes, so I will do it in 10-minute segments. What's happening? Okay, so let's start with Alan Turing. 1951 or 50. He proposed the Alan Turing test before he died, or before he committed suicide, unfortunately. So the imitation game basically goes on. When you ask a question to the computer or the human being, do the answers match? Are they indistinguishable? That's a very simple test. That's the holy grail of AI. I'm not teaching anything new. I'm just recollecting the past. Then the question comes in, how is the great DARPA, which basically funded all the great research in this country, right, your cell phones to internet, how do they define this AI? The term AI, essentially. So this is their definition of AI. So we have to have the taxonomy clear. So the taxonomy is, they define the first wave as handcrafted knowledge, pretty much. Basically, you define an algorithm, and the algorithm explores various possibilities within the confines of the algorithm. The second wave is currently what we are experiencing, the deep learning, so-called. Basically, it's a statistical learning. That is, you observe, and you learn from it. But you are not able to abstract and reason from that. That's basically the second wave. And the third wave, they are saying contextual adaptation, basically the causal AI. That's what we are going to talk about it. So as to further strengthen it, first wave is basically the knowledge is defined by the humans and the specifics are explored by the computer, basically the algorithm. The second wave is basically engineers create your own interesting kind of networks, and essentially try to do statistical learning. You can call it overfitting, underfitting, or generational adversarial network, and all kinds of stuff. Then the third one is the answer H and answer C, the human and the computer, is indistinguishable? Can it pass the Turing test? That's a holy grail. So let's see the actual examples. Yes. Long back, IBM demonstrated, basically the Deep Blue won against Gary Kasparov. And we have plenty of examples yesterday, today. We have seen a lot of examples how they are going to replace pathologists. Will they replace pathologists? That's a debatable topic. And we were reminded, fortunately, by a few doctors, AI is not going to replace them. It's about humans and doctor interactions. So I'm not getting into the debate whether the tech geeks are going to win the game or not. I myself, being a tech geek, I'll tell you my story in a second. So that's the story today. So the future is the emerging area. So can we reason? Can we abstract a model from the data? And if we have to abstract a model from the data, we need a language, we need an expression, we need a mathematical machinery. All the three things are needed. That's what the theory of causality is. And that's being heavily funded by DARPA. DARPA is challenging it. They are not happy with the current state of affairs. They want the defense systems, the soldiers of the future, to have the machines that can abstract and reason. That's the key. And how can we apply it to health? That's another question. Because we heard the current AI they're not going to accept, and the doctors are basically taught in an Australian way. So let's stick back to human health. So that's basically the fast intro. If you really look at it, 15 years ago, if somebody had a cancer, what the doctor did? A biopsy, a CT scan, and a basic blood work, and they defined whatever the protocol says, they prescribed it. It didn't work. Many people die. I mean, cancer is still a big problem. And it's not the leading cause of death, but it's come close. Now what's happening today? We have repeat biopsies. We have many panels. At least genomic medicine is taking off. And the holy grail is, can we find all the mutant genes and find all the aberrant pathways? And can we stop it? Can we do something about it? Right? That's what is today. And we are getting into the transcriptome, plasma-based mutations. And the future is more interesting. There is going to be a lot more genomic testing, a lot more mutational testing. And there's going to be immunotherapy and a whole bunch of things coming in. So what it all tells us is one simple thing. Let's look at it. This is from the Institute of Medicine. Human capacity. The doctors are basically think causally and have the relationship, what it is, and they have to get into their brain a mechanistic model of what they are going to prescribe. They are not going to be slaves to the machine. It's not going to happen. But if you look at the reality, we are basically going to have too much of data. This is a logarithmic scale. I basically put it in a logarithmic scale. And how is the doctor going to understand all these data in their brain and sit before the patient and give you a prescription? It's a dilemma. They are also struggling with it. What the machines can do. Can it be an intelligent assistant, or can it be a black box magic that gives the solution? So let's look at how the doctors are trained. The doctors are trained in an Australian way. Basically, they have a DX, which is how that's a taxonomy of symptoms. And then they do RX, basically the algorithms. That's what they have been taught in a nutshell. You go to talk to any dean, any academic medical center, that's what they do. Can you fit your deep learning models or the future of causal AI into this model? If you don't, we are toast. That's a key question. That's where it comes down. I was reminded, thankfully, by a few doctors yesterday and today, essentially, read the last sentence. AMA House of Delegates use the term augmented intelligence. Basically, as a conceptualization of AI, it's an assistive role. So can we make our AI assistive role? The theory of causality, a mechanistic model. Can we create a mechanistic model for the doctors? And let's take cancer as an example. That's what I'm going to take into the last piece. So this is the first piece of defining the problem. Now, having said the holy grail of AI, defined by Alan Turing, and what the medical community wants in the case of cancer, let's look at what the tech geeks are saying. There's a lot of tech geeks in the room, I guess. How many of you are from tech field here? Okay, beautiful. When you see the tech field, let's start with Alan Turing, 1950. He started the mathematical machinery of computers. He defined it very early on. And we had, and I just chose 1975 as a starting point and looking at probably, 40 years of computing history? And you can see a striking similarity here. The first generation, everything was hunky-dory, linear line. By the way, this is a logarithmic scale. With a single core on a CPU processor, we were able to get linear performance. The transistors were going up. Everything was great. Whatever my grandfather wrote a program here will run faster here, because all we did was increase the frequency. Great. then there is a little bit of hell broke on the planet. You see the slopes becoming different because we are hitting the power wall. I spent my life entirely on this, 35 years in my career. That's it. And then we said, wow, it's hitting the power wall. What can I do? We transitioned to the multi-core. So these are my products, actually. I was the architect of all these products. Guess what? What's next? This is not going to stay. Technology doesn't stand still. All the geeks are going to be pushing the boundary. Then the question comes in, let's look at the software story. We saw the software story, and we need to merge this. First wave, pre-programmed, basically rigidly programmed. First wave is defining the DARPA terminology. Second wave is statistical learning. And you can see the statistical learning coinciding with multi-core and GPUs, basically. Essentially heterogeneous computing, whatever we want to call it. And what's next is going to happen. The question is, this is what is about to come. How do we make this useful for human health? That is an interesting question. Okay? What do we need then? Now let's define our problem. I've laid out the 3 foundations, and if we have to tackle cancer, we just can't tackle the cancer just basically using electronic health record. There is no way. We need to understand genomics, omics in general, all the way to transcriptomics, proteomics. And we need to understand the images, whether it is H&E or immunotherapy, fluorescence imaging, MRI, doesn't matter. It is. There are 3 different modalities. That means we need to understand and aggregate the data at scale. And cancer is a disease of n equal to 1. It's a heterogeneous disease even among one single person. Then that means we need to compute. This is just storage at the bottom level. Then how do you aggregate all these pieces of data, break the silos between them, and essentially annotate and analyze that? Can we do it just with the deep learning, or will the doctors understand it, or you need a causal learning? That's where the key is. And there is some hope on that. So this is where the future is trending. And then there is another class of problems, because clinicians are basically don't have time to do research. If you have to solve the problem, somebody has to slog on the science area. So we need to basically expose the similar data both to the researchers and the clinicians. So this is the stack looks like. This is the framework we need in order to solve the problem of the tackle. This is where the future lies. So that's so far for the first part of the 10 minutes. Now, let's define the causality. So we talked about causal learning. We have to go there. What's causal learning in a nutshell? How many of you heard Simpson's paradox? I'm sure you'll know. Thank you. Great. So let's do a small quiz. I just took the data, half of it. People who exercised, a notion of exercise, how many hours you exercise, and the notion of cholesterol. Plot it up. Take a small example. This is the data. You use a probability theory. All of you are trained probability. You know probability very well, statistics reasonably well. Fit it. What does it say? So the point is, data has something to say, but if you strictly depend on data, we are toast. We come to a wrong conclusion. So we need a story behind it. So what is the story? That means you need to have a notion. So we as human beings have an abstraction of something. That abstraction of something can be, I'm just approximately showing it in a form of a directed acyclic graph. Let's use the terminology, mathematical term, DAGs, basically. They're not cyclic, but they are acyclic. That's what I want to do. Then age is a confounder of exercise and cholesterol. If you marry this particular conceptualization into this data, you can reason, differently. The data segregated by this graph. So this is a causal story. So the whole point of the exercise of causality in a small one slide is essentially reflecting the model on the data and refining it with the data. If you don't do that, I heard this talk today, Stephen from Houston was really telling about it. But I asked him, hey, have you done the theory of causality? He was a chip designer, so it's kind of interesting. So we exchanged notes and then say, yeah, give me about it. So the good news is this has been very well developed, actually. Turing Award was given to the person, Judea Pearl, in 2011. So he is basically, and he was also the founder of American Academy of Artificial Intelligence. He was the founding member as well. Anyway, so what I'm trying to say here is a segregated data is good. Now, what's Simpson's paradox? This is a very simple example. Let me leave this, Simpson's paradox. This is 1951. It's way back. And he took it to 700 patients. And this was troubling many statisticians for a long time. You look at this very carefully. They took men, women, and basically they were given drugs, and some were no drugs, and the recovery rate was recorded. So it's basically gender, people who took drug or not drug, basically a trial, and do that. And very interesting observation here. If you look at the combined data, 78% recovered taking drug, 83% recovered without taking drug. But you segregate it by men and women. Guess what? They both benefited. So if you know the gender, you can prescribe. If you don't know the gender, you cannot prescribe. Juxtapose it with the Oslearian model, Oslearian ideal, DX and RX. It doesn't make sense. The partition by gender, more men recover who take it, so do women. So should the doctor prescribe for men and women or unknown gender? That is a fundamental question. So this is a textbook example. I did not cook it up. This has been there. Everybody has been taught in all the universities. So the whole theory of causality in a very simple way I can describe for an afternoon is we need to understand the story behind the data. We need to understand the story and a way to describe the story. That is, we need a mathematical machinery and a notation. Both we need. If we have a notation to describe the story and a mathematical machinery to work on it, and we can crack this nut. That's about it. How do we crack this nut? This is the primer. So pardon for me if those of you who know this, I apologize, but those of you who don't, it may be an interesting, a quick primer. So as I told you, the basic notation is directed acyclic graph. You take the gender, and then drug use. If you use drug, it may recovery status. So let us say Y means successful recovery for the time being, because the recovery depends on various levels. But for the purposes of primer, I'm just using 0 or 1. X1 means they take the drug, X0 means no drug, and Y1 means they are recovered, and Y0 they did not. Then the question here is, how do they? Then I introduce a notation for you. Do X equal to 1 means they are taking drugs. Do X equal to 0 means they don't take drugs. So I said there is a notation, and we need a mathematical representation for the machinery to operate, like the way Alan Turing did his imaginary computer in 1947. Now the next question is, what's our task? This expression should be self-explanatory, but I'll go through it. Probability of people recovering, taking drugs, minus the probability of people recovering without taking drugs. That is a random trial. In a nutshell, RCT, the golden standard that the doctors will sign on. Now we are making this magic. We need to have the clinicians sign on to the next generation of AI, otherwise they won't use it. So we have to speak their language. This is random controlled trial couched in the language of causal theory is average causal effect. Are you with me? Okay. That's the maximum math. And there is one more math I will do. Now, how do you solve Simpson's paradox? Our task is to estimate the average causal difference. If you use the average causal difference, can you disprove whether I can prescribe to men and women, but if gender is not known, I cannot prescribe? You need to crack that particular thing. Then we have solved Simpson's paradox. Let's do that. So in order to do that, we need to conduct a random trial. Unfortunately, we don't have more money. All we have is observational data. Can you conduct random trial on an observational data? That is the magic of the mathematical machinery we are going to introduce. If I get one thing out of it this afternoon, that's the one thing. I'm going home happily to Portland after that. Okay, so let me flip that. That means, for those of you, are there any economists here? Okay, you have used structural equation models. Okay, so you are not a microeconomist. Okay, that's fine. So economists have been using this for a long time. They use structural equation model, but I'm replacing the structural equation model with causal structure, graph causal models, GCM. That's what I'm using the word GCM. This is structural equation model and graph causal model. Graph causal model is nothing but a directed acyclic graph. And essentially, for those of you, how many of you really understand graphs? If you think you don't understand graph, here is a simple test. You guys understand graph. You know how FedEx runs, how the United States Postal Service runs, traveling salesman problem. It is basically being used for a long time. You know how chips are designed, electronic chips? A whole bunch of graph theory. So there are enough people, the graph theory has been there in existence for more than a century and extremely well developed as any algebra, basically. So it's not a new science. So I just want to demystify that, essentially. So let's do that. Modified model is then, what I'm trying to do is the probability of Y recovering given various kinds of medicine at various levels, dosage. That is basically the general structure of the expressions, the do calculus we are getting into, couching into. That means I have to do a graph surgery. What if I take the graph and basically force this function to be 0 or force this function to be 1? Then I'm conducting the trial on this graph. Okay? So that's the first magic transition. Now, once I transition that, then let us do probability of people recovering, taking drugs, is this expression. This is the theorem. If you really want it, I'm more than happy to go over it. That's a 1-hour class. I can derive it from first principles, even now, or both. But you can take it for granted, and I will tell you the book in a bit. Now, we have done the graph surgery here. The next piece is interesting. Let's substitute using this equation the data from this table, and you can do probability of people recovering, taking the drug is 0.83. I'm not pulling a magic, just using the same data here. The probability of people recovering without taking drugs is 0.78. Now, average causal effect is positive. Simpson's paradox, what we talked. We can't prescribe if you don't know the gender. That is based on statistics. Now I'm using the modified statistics, which we are calling it a theory of causality, and we are basically coming out with the solution to the Simpson's paradox. So that's the essence of it in a nutshell. And how are we going to use it in medicine, in cancer? That's the next question. The last 10 minutes, I'm going to get into it. For those of you, there is a popular book. You can read it. For those of you who don't want to do the popular book, you can take his graduate's book, Causality, which is a nice one, which he spent. And for those of you who really want it, I'll put my email and I'll send you the technical report, which is much better, which is only 40 pages, but it's still good. So he got the Turing Prize in 2011, by the way. And he's, we all know correlation is not causation, but I hope you got what causality means. X causes Y. And if X causes Y, can you measure the causal effect? And how do you measure the causal effect? And do you have an expression? Do you have a machinery? Which I just showed you a few minutes back. Now, how do we apply this? We heard speaker after speaker talking about, yeah, I can do deep learning. I get as close as to a pathologist. But if a noise comes in, I can't tell you. There is no mechanistic model in the statistical learning. So that's why DARPA is absolutely serious about going beyond the deep learning. It's DARPA who funded this deep learning. Even Glenn Hinton, Yakun, everybody got the money from DARPA. Now DARPA is throwing a lot more money on what is next, and they are basically going there. So we took a small case study just to illustrate the problem and how we can get a solution. I just made this. Let's revise before I get into my real case study. First generation, second generation, and third generation of waves, and there will be fourth and fifth. Intel now sells the 10th generation processor, so what? They make a generation for every year. That was my past life. So first generation, it reasons over a narrowly defined problem, no learning capability. The second generation perceives the data based on scanning the picture and learns from it, basically. But it is no way of abstraction or reasoning. The third generation, how can we do? Suppose we want to apply to cancer. Okay, so basically then we have to understand the cell signaling pathways. A lot of work has been done by the biologist, sweating over late nights in the lab. So let me put a simple picture. So this is basically, that is the cell surface and signaling pathway. Put those of you here. And now, can I take that information? Can I take the patient preferences? Can I take the cost and availability and diagnostics, the real world? All these are affecting because you can't just go to a hospital and demand the best medicine unless you can't know how to pay for it. And then the personal preferences or choices too is cancer. And then we talked about directed acyclic graph. How do you represent the lifetime? There is Rx and Dx. You go to the Oscillarian principle and lay it out. A treatment, various treatment, whether it's cured or not. Again, you measure your treatment time series. It's a Markovian chain. That's a model of applying causal theory for that. So that means one little thing. I'm going to connect this to what I said originally. Remember, this is not just electronic health record. We are talking about genomics, we are talking about imaging, we are talking about radiology, everything. It's a multimodal. That means, that's why I laid out, unless you have a framework to combine all the data and break the silos, we can't practice it. So in order to practice any causal application, go beyond deep learning, even deep learning, right now what we are doing today is trying that on silos. But if you want to go to the next level, it's more complicated, but at the same time, you need to have a framework. If you have a framework, we can support all kinds of models too. So I just took an example, and essentially these are, I took a sample of 300 plus patients who have been treated for prostate, and this is actual data. And I'm just wanting to give you a number. I'm taking 141 members patients with post-therapy PSA measures who had complete remission, partial remission, progressive disease, and who had surgery among them. I have to leave out 2 more people. These numbers are clinical data, actually. The data is good, but that's not the point here. And the key fact here is, for causal modeling, I took 136 patients, and essentially who had a decrease of PSA level. PSA level is the measure of prostate cancer. How do you model it? Multi-dimensional data aggregation was there, so I have a few more minutes to get into it. So there are 3 kinds of data we talked about. Electronic health record or lab, they are all relation database, which can be represented. The pathology and radiology is a bunch of pixels, or whatever it is. And then the genomics is a bunch of letters, ACGT, or 16 letters of proteins. Now, that's the modeling. I'm just giving you. So here you can see deep learning is used for radiology sometimes to identify some spots and things like it. And then we can determine the PSMA levels. But whereas the EHR is very much more where you see the preferences of the patient and the cost and the doctor and what kind of therapies you need to do. And essentially genomic sequencing determines whether actually what's happening at the aberrational level. Now, putting all together, basically what we want is a better patient outcome, right? So we did that. I crunched the numbers. So before I declare victory or partial victory or a path towards a partial victory, let's work it out. This is a data insight of one particular patient. That I can't present all the 441 patients, but just take one example. This is a patient where basically he had 2 surgeries, pretty radical prostatectomy. This is pretty devastating surgeries. Basically, it's castration in simple terms. And this patient did not recover, so finally they ended up doing Theranostics. I will tell you what Theranostics in a few slides down. And the question for us is, we are applying this model, time series model, Markovian chain, directed acyclic graph. You have a diagnosis, you find the disease, you do the treatment, and one of those things you choose, and then observe and treatment. So for sake of space, I compressed a lot of the information into a simpler graph. Now the key question you want to ask is, that's the actual this patient took. This is the path took. They went to the surgery here. The surgery is defined 2 surgeries and then didn't work. And the PSA level was still high. Then they went to Theranostics and this. The key question we want to ask a causal question, because we talk about causality and the mechanistic model that the doctor wants to understand. Remember, the doctor can understand 10 things at a time in his head, not 1,000 things. So the choice of the treatment can be done. I didn't have enough data, so I couldn't model this. But I can answer the question if I have enough data and enough collection. I chose to for the illustration purposes. The next question here is a counterfactual question. Having done, this person has gone through surgery and then Theranostics, what would have caused the choice of Theranostics rather than surgery at T1? Can you have gone to Theranostics itself? It's a counterfactual question. I don't have the data in this particular thing. But it's not all is lost. The last question I have data. Could Theranostics have been successful instead of surgery at T0? Because the data I presented, I have information to tease out this. The same way we teased out the Simpson's paradox, just for illustration purposes. The answer is yes. Then you're going to ask me, hey, show me the model and show me the data, right? That's the next slide. That's a simplified model. The question we ask, the counterfactual question, is disease staging is important. I got the data. Surgery, we had the data. The Theranostics, we had the data, and we have the data of the response. Probability of response doing Theranostics alone for these people is 0.37, 37%. Probability of response doing Theranostics and prostatectomy is 0.27. And guess what? Then the next question is, the medical community asked me, show me the evidence. Here is a paper by Kulkarni. It's a Kulkarni's paper, yeah. So we validated that. This is a real thing. So this is the same thing I'm giving the talk. I gave the talk in prostate cancer retreat last week at San Diego. They were all, it was room full of doctors, basically. So I can't just get away with it. So that's pretty much. So the key point I'm trying to make here is the future is interesting and bright for those of you wanting to pursue data science. We have to mix a little bit more mathematics. It is not going to be lazy AI. So I've been warning, because I'm a guy who worked for Microsoft and Intel, and I'm not shy of saying my experience. I was the chief architect of Xeon servers. Those of you who know what Xeon server, for 15 years, my job was every year I have to come up with a server architecture and get it done that doubles the performance at the same power envelope and the same cost. So it's a demanding one, working about that. So the same thing is, if you really want to address these things, we can't just simply take AI and feed you to TensorFlow and happy, go home. Okay? We have to have some notion of what we need to do in the causal theory. So given that, this is the Theranostics. For those of you, this is for light entertainment, how the Theranostics work. Basically, that is, you basically cancer cell, you put a radioactive material, and it's basically diagnostics. And when the diagnostics happens, the emitter, you can trigger the emitter, and essentially you can do the apoptosis. And this has been done, and the survival rate is pretty good. This is basically being pioneered in Germany. Is about to come here, so that's how it works. This is a Gleason score of a prostate cancer patient with a PSA level of 4.6, and that's metasized, having conventional surgery. This is a real example. Hormone therapy, see the metasize. And then they were given the radiotheranostics, MTRT, radiotherapy, basically. Metasized treatment of radiotherapy is the MTRT. Look at the PSA level. So, thank you. Any questions?
Excellent. Thanks so much, Gans. And I think we have time for a couple questions if we have.
So, is there a specific class of questions? If I understand, I mean, I'm a physician. We would be worried about confounding in a lot of these kinds of studies. Are there specific classes of questions that you're able to address? Can you characterize them in a simple way that, oh, I am able to look at this question but not this other question?
Yes, because that's one of the things we need to work with you. At the end of the day, causal theory doesn't stand alone. It's not standalone with the data. I need to engage the clinicians even to come up with your first graph model. It could be completely wrong. Don't get me, you don't have to get the right model, but you need to start with your model. All the data, all the specific kinds of data has to be represented. Then if you have enough data, I can see whether your graph and the data congruent using directional separation, using all the graph theory theorems. Graph theory has a, how many of you know Coinsberg problem, the original Eulerian problem, that when Euler solved the problem of 7 bridges, how do you cross the 7 bridges without, retracing your path? So that was a graph problem. That was, 1800, I guess. So yeah, if I work with you as a content expert, you the doctor, I'm an engineer, I'll bring my science to you, my trade skills to you, you bring your trade skills, and at the end of the day, you are responsible for the patient at the end of the day, right? And you are not going to prescribe something that causally appeal to you. There is a mechanistic understanding of what you are going to prescribe. That's what we are going to construct. So your question is correct. That's a fundamental question. I hope I got that one. When I put those graphs doesn't come from me. Come from the domain expert, rather.
Thank you again, Gans. I'd love to take more questions, but we're going to have to move on to our next session. So round of applause again. Thank you very much.